Last class, we looked at how to write an equilibrium constant expression based on a balanced chemical equation, and also how to manipulate the K values as we manipulate equations. Today, we're going to look at a single equation and look at how we calculate K values and also how we calculate equilibrium concentrations. So to do this, we're going to use something called an ICE table. So to use an ICE table, we look at three different pieces of information. We look at initial concentrations, we look at changes in concentrations, and we look at equilibrium concentrations. Thus the acronym ICE. So let's take a look at a couple of examples. This first one is pretty simple. You're given equilibrium amounts of everything, and you're asked to calculate Kc. So whenever you're asked to solve an equilibrium problem, the first thing you want to do is write your equilibrium expression and leave room underneath to set up your ICE table. In your ICE table, each reactant and product is going to be a separate column, and your three rows will always be initial amounts, change in amount, and equilibrium amount. The other thing you want to do is write the K expression for the specific reaction. In this case, the K expression looks like this. So now we need to fill in values. Since we're given equilibrium values, we're going to look at this row right here, the equilibrium row. Now you notice we're given number of moles in a 10-liter container. Moles divided by liters is concentration. So the concentration of SO2 is 0.0250. That would be 0.250 divided by 10. O2, the concentration is 0.0200, and SO3, 0.0162. Now that we have our three equilibrium values, we can plug them into the Kc expression. Make sure you use your exponents. Don't forget them once you actually plug values in. And put that in your calculator, and when you solve it to three significant figures, you get 21.0. So that's a pretty simple, straightforward problem using an ICE table. Now we're going to look at a problem where you have to calculate equilibrium concentration values. So here's my reaction, here's my Kc value, and here are some initial concentrations, or initial number of moles in a 5.25 liter container. So again, the first thing we want to do is to write the equation. We want to write the K expression. And we know that that is equal to 54.3. And then we set up our ICE table. So 0.5 divided by 5.25 is 0.0952. So that's the concentration of H2. It's also the concentration of I2. And initially, before any reaction takes place, we don't have any products. Now, we don't know how much we produce to get to equilibrium, so that's going to be our X value. That's what we're going to call X. So in our change row, this is where we're going to introduce our unknown, our X. What we're going to do is look at the stoichiometry. So we know that H2, this concentration right here, must go down to produce products. The concentration reactant should go down to produce products. So to show that, I'm going to have a negative X. So the amount of H2 goes down by some amount X. When we look at the stoichiometry, we notice that I2 is going to go down by the same amount because there's a 1-to-1 ratio between H2 and I2. You'll also notice that we get twice as much HI as we start off with H because I have a 2-to-1 ratio. So my concentration of HI is going to go up by 2x. So at equilibrium, Here are my concentrations. Now that I have equilibrium concentrations, I'm going to plug them into the K expression. So I know that 54.3 is equal to 2x squared divided by 0.0952 minus x squared, because these two numbers are the same. Now, this looks like a nasty quadratic, and if you know how to use the quadratic solver on your calculator, you may do so. However, for all the problems I'm going to give you in class, there's a way to simplify so you do not need to use a quadratic to solve. In this case, all I need to do is take the square root of both sides. So the square root of 54.3 is 7.3485. The square root of 2x squared is 2x, and the square root of 0.095 minus 52 minus x squared is 0.0952 minus x. Okay, now I need to isolate and solve for x. So the first thing I'm going to do is multiply both sides by 0.0952 minus x. So that gives me 7.3485 times 0.0952 minus x equals 2x. Now I distribute the 7.3485 and I get 0.6996 minus 7.3485x equals 2x. Now I gather my like terms together. So I get 9.3485x equals 0.6996, which means that x is equal to 0.0748. Okay, now what is x exactly? X is the amount of change to get from initial to final. So to figure out how much H2 and I2 I have finally, I have to take 0.0952 minus 0.0748, which equals 0.0204, and that is the concentration of H2 and the concentration of I2 at equilibrium. Now, for HI, I simply take 0.0748 and multiply it by 2, because I have 2x over there, and that equals 0.11498, which really should round to 0.150 molar, and that is the concentration of HI at equilibrium. Okay, so that's how we can use an ICE table to solve for equilibrium concentrations.